This 10 to 100 turn compact Tesla coil is putting out huge energy across an arc gap. I was looking for some way to make a Tesla coil work in a more compact, usable fashion. So what I tried was take a ferrite core and put 12 turns of white auto cable wire insulated at 6.6 kV here, and then another 60 turns of thick wire just above it, which is maybe 5 more turns, which should take it 40 kV. So you can see the white wires here, 6.6, and these are the other 40 turns. And then I'm going to try to increase the 6.6 to 40. You need a spark gap which is set well with the sparks adjusted to the right distances. Also you need capacitors here, 1022 nanofarad and total about 9 nanofarad capacitance, and I'm running off 3 microwave oven transformers. Once again, this only gives about 8,000 to 10,000 Hertz per second, 8 to 10K. So we have to use some arcs to monitor it rather than wireless radiation. Here we go, turn on the sparks. Now here's a slightly bigger compact Tesla coil. We have 2 big pieces of ferrite inside, about going from there to there. Then we have about 10 turns of coated wire, like auto wire down here, slightly separate of course to avoid shorting, with about 60 turns of thick wire up here, which will go from 6 to about 50 kilovolt. Let's turn on the power now and see what happens. Here we go! That's a compact Tesla coil which has ferrite inside from the top of that wire down to the bottom of the white wire and a little further. So we have about 10 turns of white wire, 60 turns of copper wire, so it'll be about 40 kilovolt coming out over there. As a control, I would like to emphasize that this compact Tesla coil, the primary and secondary, depends absolutely on having 2 pieces of ferrite inside. I've put some mylar tape on that piece to avoid electrical shock. Now if I turn on the power, the spark gap, without that ferrite inside, nothing will happen. If I turn on this compact Tesla coil with the ferrite inside all the way from here to here, this 10 to 100 turn compact Tesla coil is putting out huge energy across an arc gap. Next we will test this compact Tesla coil with different sizes of capacitors. We're going to start with these 22 nanofarad capacitors, 2 rows of 5 in parallel, which give you 9 nanofarad in total capacitance coming into these 2 arcs. Let's turn it on. Next we're going to try it with no capacitors at all. no arc, and a very weak spark through the spark gap. Next, we're going to add one string of 22 nanofarad capacitors upstream of the spark gap. That'll give half the capacitance before, about 4.5 nanofarad instead of 9 nanofarad. Let's turn on the sparks. Again, it works, but about half as strongly as before. Now we have 4.7 nanofarad capacitors. There are 10 of them in 2 strings of 5, and that gives 2 nanofarad capacitance in total, about half what we had before. Let's turn it on and see what sort of arc we get. Maybe about half as strong as before when we had 4.5, or the strongest was 9 nanofarad capacitance. Finally, if we use just one string of 4.7 nanofarad capacitors, that'll give 1 nanofarad of capacitance in total, about half what we used before, and the arc becomes very weak. Here we have a spark gap Tesla coil, and you can see we have a bunch of capacitors here running in parallel with this primary coil here of about 12 or 15 turns. So it makes an LC circuit through the spark gap. So as we change the size of the capacitors, we should also change the resonant frequency. Let's see if that's true. To begin with, we'll line up 4 68 nanofarad capacitors, fast switching Cornell Dubilier with the primary coil. That should give 17 nanofarads in total, 68 divided by 4. And let's see what the frequency of the Tesla coil is. It's about 3.5 or 4 kilohertz. Next, we're going to use 22 nanofarad capacitors, 2 rows of 5. That should give 9 nanofarad capacitance with the same primary coil. And let's see what the frequency of the Tesla coil is now. We have 9 nanofarad instead of 17 nanofarad capacitance in parallel with the primary. Now it's about 7 kilohertz, or twice that before. Finally, we will use just 5 22 nanofarad capacitors, which will give 4.5 nanofarad capacitance in total. That's half of the 9 or 1/4 of the 17. Let's see what the frequency of the Tesla coil is now. Somewhere around 18 kilohertz. To conclude, we've got 10 4.7 nanofarad capacitors arranged in 2 strings of 5, so that'll give close to 1 nanofarad of capacitance in total, which is 4 times less than before. Let's see what the frequency of this Tesla coil is now. Very weak arc. Somewhere around 20 or 30 kilohertz. This 10 to 100 turn compact Tesla coil is putting out huge energy across an arc gap.